Hi and welcome to video 2 of 5 videos for section 10.3. In this video we're going to look at solving systems of linear equations using that matrix. So before we do that, I want to give you some elementary row operations. So when we have a matrix, and it's key here, it's a matrix. We're not doing inverses. We're going to learn that later, and these rules or these operations don't fully apply to that. But when we're solving a system, we have these tools at our disposal. The first is we can add a multiple of one row to another. Second, we can multiply any row by a non-zero constant. So that could be an integer, it could be a fraction, it could be any value we want. Because in this matrix, remember what those are. Those are our equations, right? So as long as I multiply every piece of the equation by some number, all I do is change the way it looks. I don't actually change the value of it. And then third, if I want, I can interchange two rows. Because again, what is this matrix? It's just the system written in matrix form. So I don't have to say that equation 1 is equation 1. Equation 1 could be equation 3. It's just the way that it was written to start with, but I can really write it any way that I want. So those are 3 things we can do to help solve these systems. So let's look at an example. And we want to solve x minus y plus 3z is equal to 4. X plus 2y minus 2z is equal to 10, and 3x minus y plus 5z is equal to 14. So I'm essentially going to use the techniques we were doing in section 10.1, which is to solve for one variable and then back substitute. So when I create this augmented matrix, I have what? 1, negative 1, 3, 4, 1, 2, negative 2, 10, and 3, negative 1, 5, 14. So remember what these all represent. This is my x values, this is my y values, this is my z values, this is the constant. So if I can do some of these row operations and switch rows around to get these guys here all to be equal to 0, that means what? That means this x value is equal to some constant. So I can divide by that, that gives me my value for z. Then I can back substitute into this equation, solve for y, then substitute both of those into here and solve for x. So let's give that a try here. So what value, if I want to get a 0 inside this triangle, let's just work with the first column. Get the first column to be zeros, then get the second column. If we have more than 3, get the third column, and so forth. So if I want to get a 0 here, what do I need to multiply this first row by? So that's what I'm doing here, operation 1. Multiply row 1 by some value, so when I add it to row 2, this becomes a 0 and gives me a new row 2. So the way I'm going to write this so I can keep it straight is I'm going to say some value times row 1 plus row 2 gives me a new row 2. So I'm leaving row 1 as it is. 1, negative 1, 3, 4. So what value do I have to multiply this by? Well, if I multiply it by -1 and then I add it here, that gives me 0, right? So I'm going to multiply row 1 by -1. So -1 times 1 is -1, plus 1 is 0. -1 times -1 is +1. 1 plus 2 is 3. -1 times 3 is -3. Minus 2 is -5. And -1 times 4 is -4. Plus 10 is 6. So please, please, please be careful with your math here. If at any point, if I would have gotten one of these numbers wrong, the rest of my work is a waste of time, because the numbers are all going to be wrong at that point. So take that little bit of extra time and make sure your math is right, or else you're going to cost yourself a lot of time. All right, so that's a 0. Now I want to get this guy to be a 0. So what do I have to multiply the first row by so that I get a 0 here? Well, that's going to be -3. So I'm going to do -3 times row 1 again. We're only using row 1 to start. Plus row 3 gives me a new row 3. That's a lot of confusion that people have here. They're like, well, I'm not sure where I'm putting the numbers, and what do I keep, what do I get rid of? Now you don't have to worry about it. This tells you what you're doing. -3 times row 1, add it to row 3, gives me a new row 3. So if I do that, -3 times 1, -3, plus 3, 0. -3 times -1 is +3. 3 minus 1 is 2. -3 times 3 is -9, plus 5 is -4. -3 times 4 is -12, plus 14 is 2. So the other thing that I'm trying to do here, in addition to getting zeros in this corner, is ideally I want all of these guys along that angle to be equal to 1. So everything in green I want 0, everything in the red I want to be a 1. So let's look at what we're left here now. Well, if I can divide this bottom row by 2, right? That'll turn this into a 1, and then I could switch these rows. So basically I could multiply row 3 by a constant, which is 1/2. So I guess multiply, or if you want to think about it as divide any row. And then I could change those. So let's do that. Let's first divide row 3 by 2. So if I do that, leave 1 alone, 1, -1, 3, 4. Row 2 alone, 0, 3, -5, 6. And now if I divide row 3 by 2, I get 0, 1, -2, and 1. Again, I want 1s on that diagonal. So if I switch row 2 and row 3, now what do I get? I get 1, -1, 3, 4. If I switch them, switching these guys, I get 0, 1, -2, 1. And then the bottom one becomes 0, 3, -5, 6. So now I'm done with row 1. I started there, I'm just working my way down. So I'm not going to do anything more with row 1. Leave it as it is. 1, -1, 3, 4. And now I'm going to work with rows 2 and 3 to try to get a 0 into this box. So I have to do what? I have to multiply row 2 by a -3, because if I do that, -3 times 1 plus 3 makes this guy a 0. So leave row 2 alone. So I write it back as it was. And now do what? -3 times row 2 plus row 3 gives me a new row 3. So negative 3 times 0 is 0 plus 0, that stays 0. And it should. You better not get a number back here once you change it to a 0 or you've messed up some math somewhere. Negative 3 times 1, negative 3 plus 3 is 0. That's great. Negative 3 times negative 2 is positive 6. 6 minus 5 is 1. That's nice for us. And negative 3 times 1 is negative 3 plus 6 is 3. So we got what we wanted. We got zeros in this bottom triangle. I have ones on the diagonal. So this means what? Remember, this is my x column, my y column, my z, and my constant. So this bottom row, this guy, means z equals 3. And that's from row 3. It tells me that. So from row 3, I get 1z. If this was a 4 and this was an 8, that would mean 4z is equal to 8. And then I would just divide to get what z is equal to. But because this is a 1, I already know 1z is equal to 3. So now I can back substitute like we did earlier. Using the second row, this means what? This means y minus 2z is equal to 1. And this I get from row 2. Well, I know z is equal to 3, so that means y minus 2 times 3 is 1. Y minus 6 is 1, so y is equal to 7. And then lastly, from the top row, I have x minus y plus 3 is 4. 3z is 4. I know what y and z are, so that means x minus y, which is 7, plus 3 times z, which is 3, is equal to 4. So x minus 7 plus 9 equals 4. So x plus 2 equals 4. So subtract 2 tells me that x is equal to positive 2. So after all that, I got my zeros in the corner, I got ones on the diagonal, I back substituted, so my answer as an ordered triple is that x is 2, y is 7, z is 3. And that is my solution to this system of linear equations. So again, you could have done them all separately using substitution, elimination, what we learned in 10.1, but using matrices helps keep it a lot more organized, and as long as we use these elementary row operations, makes the math fairly straightforward for us. So what I did here, this process of taking the augmented matrix, getting zeros in this corner, getting ones along the diagonal, this is what's known as Gaussian elimination. So if you're given a problem and it says solve by Gaussian elimination, that's what this is, getting zeros and ones and then back substituting to find these values for the other variables. So that's it. That's solving a system of multiple variables, in this case 3, using a matrix, using Gaussian elimination. Just one example on this video. It was long enough. If you need to go back, follow through, that's certainly fine. Otherwise, come on back, and we're going to look at what's known as row echelon form and reduced row echelon form in video 3.